All right. So this part isn't directly related to what's on the assessment, but to have a foundation of knowledge of the different types of data structures out there that are commonly used uh, is good for you to have in your tool set. So whenever they do come up in interview questions, some of the solutions to these technical interview questions, you'll want to use one of these data structures that you might see. So it's good to have in your tool belt, but we don't go that in depth in data structures right now. We will cover them later in the course, towards like pretty much near the end when we're talking about interviewing and interview prep, when we go through our interview boot camp, which is like a 2-day thing towards the end of the curriculum or end of the course. But I just want to introduce you to them because now, just because the earlier the better, we're in the process of creating our own data structures currently with the challenges. So here's a quick quote from the author of Python. It's easy to make mistakes that only come out much later after you've already implemented a lot of code. You'll realize, oh, I should have used a different types of data structure. So then you have to start over from scratch. So again, as long as you know these different types of data structures exist, you can kind of pick and choose which one will be the best data structure to solve your problem. All right, overview. What is a data structure? Why are data structures important? Data structure examples. We're going to go over linked lists specifically, and we're going to do what are linked lists, and then we're going to do a live coding session of a linked list. So what are data structures? It's essentially a way you organize your data. So over the past 3 to 4 days, with the introduction of object-oriented programming, we've been creating our own data structures. So for like the school interface, we've been creating a student data structure. We've been creating staff data structures, a person data structure, a school data structure. The classes you've been creating, they are data structures. They're just very specific to what you're currently building. These are more broad data structures, what we're about to cover, that exist in the world and are pretty common. So a data structure is a collection of data values, the relationships among them, and the functions and or operations that can be applied to them. So just like your school data structure that you currently have, it has some data in the init initial instance variables that you create. So like an array of array of students, an array of staff. It also has instance methods on that data structure, on the school data structure, like grab all the students, adding a student, deleting a student, and you can continue to add on different functions and or operations onto the school data structure. Does anybody have any questions about what a data structure is right now? We've already been creating them. These are just more very common types of data structures that you'll encounter at some point. So why are data structures important? Using the right data structure will help your software run more efficient, help you manipulate or change data more efficiently, help you scale your application. So depending on the type of data structure you use, some data structures are better used for specific types of scenarios like memory management, speed, and other attributes. And it just helps you become a better engineer because you have the knowledge of what these data structures are and what the use cases for them are. So essentially just makes your software more efficient. So data structure examples. So on the left, we have our data types. So that we should be pretty familiar with: strings, numbers, arrays or lists, objects or dictionaries. We have Boolean values, null, none, and undefined. And do you know that power button that you kind of see underneath the data type? The power button symbol literally represents a 1 and a 0, which is a Boolean value, like true and false. Just a little fun fact. On the right side are very common data structures that you may see in the future out there when you become a software engineer. And it's just good to know what these kind of are. So arrays and lists, and objects and dictionary, those are in fact data structures. We have stacks, queues. We've kind of covered what a stack is. We'll kind of get a visual representation of what that looks like, as well as a queue. We have linked lists. This is where the data structure starts to get a little more complex because we're dealing with essentially nodes, and it gets a little more complex when linked lists is like the first element, the first data structure where things start to get a little more complex. Binary search trees, hash tables, tries, min and max heaps, and there's plenty more. So a data structure. So here are a couple of visual examples of what a stack, queue, and a linked list looks like. So we kind of covered stacks earlier. What is a stack? Can someone tell me? Adam, what is a stack? Chase.
So it's just a data structure that works on the last in, first out principle. So items that you put in first are going to be removed last, and items that come in later are going to be removed first.
Yep. Yeah. So it's essentially a data structure that is an array that only operates in the last in, first out principle. So it has specific methods in the stack data structure that inserts an element to the very last, like at the end of an array, and then it also has a method that removes it from pops it off the last element from an array. And then there's queues, which is essentially the opposite of a stack. We have insert and remove. So it operates in the first in, first out. So the first one that you insert into the array or into the queue is the first one that will exit the queue. And so this insert and remove, or can you guys see my mouse or no? Okay, yeah. So insert and remove are like methods in the stack data structure. And then in the queue data structure, there's a dequeue and enqueue method that inserts and removes. But now we get to the linked lists. Linked lists are a little more, like as I said, complex. And this is the first time we're seeing these things called like a head node. We're seeing these things called nodes, which we haven't seen before. We have this head node, and then each node consists of multiple like data. So a linked list is essentially consists of multiple nodes, which in itself is its own little data structure, pretty much. Can anybody tell me what a node is? Does anybody know what a node is?
It's basically just an array or a list. And then you can contain in like an object in the first element. And then so just the way it's kind of broken out on the picture, the first element in this list would be your data object. And then the second element would be the address to point to the next object in the list or the next link.
Yeah, so a node is essentially just a point of data within your data structure. So
you said stack was like an array. Is node its own thing, or is it its own class, or is it something that we make?
Yep, it'll be its own class. And yeah, so the head node has some data in it. We can actually put kind of exactly whatever kind of data we want in here. And then it also has a point, like another data point that contains the next node in the list, in the linked list, which points to this node, which then points to this node. So why do we have all these data structures like linked lists and then everything like that? So all these data structures have been created throughout time to solve problems. So linked lists, the linked lists exist because of a problem that occurred in memory management. So the problem, for example, if I create an array, let's say it's called array 1 that consists of 6 values, 4, 7, 2, 8, 6, and 9. That memory is, that variable array 1 is stored in memory, which is represented down here. It's a visual representation of RAM, so your random access memory on your machine. And each one of these yellow blocks is a memory address. Just think of it as like in your neighborhood, on your street, a block of street. Each house is a memory address. And when we store this array 1, each element, each number must be stored all next to each other in the memory. So at each one of these addresses, right next to one of them is stored 4, 7, 2, 8, 6, and 9. And the problem is, if I create another random variable called int1, and it's assigned to 5, and it randomly assigns it next to the address where array 1 is down here. So 5 just happens to randomly get assigned there, moves in right next to array 1. And then I decide to push in another value into array 1. It has nowhere to go because array 1 always has to live right next to each other. All the elements within the array 1 have to live right next to each other. So when 1 goes to be pushed into the array, it wants to come in right next to 9, but it can't because 5 already exists there. So what they has to do is completely remove that from memory and then find another block of addresses where 1 can reside. So, and that's not that efficient, having to delete and reassign everything. So, but what happens if array 1 comes in, and then all these other integers get assigned randomly in our RAM, and then I decide to have 1 get pushed into the array. And there's no space for array 1 to have the 1 appended to it in our RAM. So there's no more memory where array 1 can be stored, and you'll get an error. Does anybody have any questions about kind of how this works? So that's where linked lists come in. If we convert this array into a linked list, here's a visual representation. We have our data and then a next node. So a linked list can store the head node that takes up 2 spots of memory, one for the 4 and another part of the data that points to the next node. And so if I wanted to add 4, it just gets randomly put right here, takes up 2 spots. Then if I wanted to add 7 just randomly gets put over here in RAM. If I wanted to add 2, it just continues. 2 gets added here. It just randomly puts the node in RAM where there's space available. So when we wanted to add 1 before, we didn't have room in this scenario because there wasn't enough space to hold that array 1. But if we convert it to a linked list, there is space now. So it's all about memory management.
If you extended your house address metaphor, it's kind of like you're a semi-gypsy nomad, and every time you move, you leave a forwarding address, right? Yep.
And this node, this other piece of data, this next node, that just points to the other address. It's like, I like to think of it, it's like, before we all used to, in order to talk to one another in here, we all had to live right next to each other as a community. But now we have like telephone lines that connect all our houses, and we actually know the address of where the other person lives. So now,
doesn't that use more memory?
it uses more, it uses more memory, but each node, it allows you to like use little chunks of memory instead of having like one big chunk of memory with an array. And there are other limitations to linked lists. So let's actually start creating a linked list. Where to go? All right. Desktop. Make directory.
And while he's doing that, I will say, spoiler alert, I watched the YouTube video early today, and for anybody who's confused about stacks and queues like I was, it's a stack is like a stack of plates, just like you store them in the cupboard, and a queue is like lining up to go to the theater. And once she used that in her YouTube video, I was like, why have I spent my entire adult life confused about those concepts? So.
Yeah, I like to do like the pancake example for stacks, or a stack of paper. You just add the pancakes on top, and then when you take them off from top. And then, yeah, queue with the theater line. I like that. So I'm going to touch linked list.py code. So with linked list, let's look at here. So linked lists have something called a node and the actual linked list. So let's create a class linked list. I'm just going to pass it right now. And then I'm going to also create a class node. I'm just going to pass it right now. So in the node class, we have some sort of data, which could be pretty much anything. It could be a string, be a number, but more often than not, they're numbers. And then we also have a next node. So we can literally, in our def init, we can do self, we can do data, which is assign it to none for right now as a default value, and next node, and assign it to none right now as default. And we have self.data equals data, and self.next node equals next node. And that's all we need for our node class. Now, for linked list, we need to, in our init, the only thing we're storing in here, in our linked list, is the head node. And we're going to assign it to none right now. Self.head equals none. There's other things we can store in here, like the length of the linked list, if it's a doubly linked list. So yeah. So we can also store the length. Let's actually store the length too, just because we can. But just know a linked list has a head node and some attributes, some methods where we can add it, like add node. Can add a node. And we can delete a node or remove a node. Pass. So in order to add a node to a linked list, well, let's actually first, let's create a new linked list. So we want, just like we've been doing with objects, we have to create an instance of a linked list. So we can say like new linked list equals linked list. And right now we're we're just creating a new instance of a linked list. We're not creating any nodes. We're just creating a linked list. So an empty linked list. And we can print this. Let's print this. Print new linked list. So I'm down here. I'm going to Python linked list. So I've got my linked list object. Great. Now, if I wanted to print the head to see what the head node is, I can clear. Right now, we don't have a head node. So in order to do it, we need to add. How do we add data to our linked list? So if I wanted to add some sort of data, let's convert this 4726 or 8691 to a linked list. So I need to add some data. And then what do I need to do? First I actually need to create a node of that data. So I can say like new node equals node and pass in the data. And so the first time I add a node to my linked list, it should be at the head. And then every other time it should be like appended to every single, essentially the next node. So the first thing I need to do, I need to say if self.head equals none, self.head equals new node. So that's the first step. All right, so we have our new linked list. Let's print, let's not print, let's create a new node, or let's add to our linked list. Linked list dot add, and I'm going to add, what's the order? 472. So I'm going to add 4. So if I run this, cool, nothing happened. But I want to print new linked list, and I want to print the head dot head to see what that looks like. All right, so the head is now this node object that I created up here. So this add method takes some data, creates a new node instance, assigning it to new node, and it's doing some logic here. It's saying if the self.head equals none, assign the head to this new node instance. And that's what this looks like. But now how do I actually look at the data in head? So I can do new head or new linked list dot head. So this new head or this head is a node object, and inside the node object, I have access to this data. So I can do dot data to see what it looks like. There we go. There's my 4 that I just added. I can also test to see what the next node, which should be none because I've only added 1. Cool. Now I want to add 7. So if I wanted to add 7 and 4 already exists at the head node, now I want to, this is where like kind of the logic of traversing data structures gets a little confusing. So we have a head node already. So now what do I need to do? So else, I can say like, so from like a logic standpoint, if the head node already exists, then I have to move on to the next node. And what if that node exists? Then I have to move on to the next node. So it's literally just, I have to go all the way to the, so I essentially have to go all the way to the end of the linked list. And how do I do that? So I can do I want to keep track of a current, like what current node I'm on. So current node equals, I'm going to start at the head node because that's the only way you can traverse a linked list. You have to start at the head because this is where it starts. So current head or current node equals this dot head. And then I can do, say,
Make it
while,
self.head. You got a JavaScriptism in there.
there we go. Self.head while current node. So I just want to print something. Print current node. And I'm going to comment that out. So when I add 4, it should be good. And then when I add 7, it should actually come down here and then print the current node. So clear. I actually want to print the current node dot data to make sure I know specifically what node it is. So here, the current node's data is 4. The next node should be what? None. All right. So I can say, wow. So if the next node has a value, then I need to move on to the other, like the next node after that, and just keep going. So I can say, wow, current node dot next node equals like it's something. So if there's a value here, how do I do if there's a next node value? I guess
Not none.
not none. All right. Well, current next node. So while it's not none, I need to move on to the next node. So I essentially have to reassign the current node to the current node's next node. Current node dot next node. And then once it does equal none, it breaks out of that while loop. And I can say current node dot next node equals new node. And I can just return the new node. So let's walk through this. So let's print. So right now I'm printing 4, or I'm adding 4. I'm printing the head data. And now I'm adding 7. And now I'm printing the head's next node. So I'm going to print that. Uh-oh, not none. Does that not work? What if I just did that? So if the current node dot next node, if it has a value. Okay, that worked. So while the current node next node has a value, come into here, reassign the current node to the current node's next node. So I'm clear it. So the linked list object, I'm printing right here. I'm going to delete that. I'm adding 4, which is here, and then I'm printing the head's next node, which is down here. So what is this value? I can do the next node dot data. So there. If I wanted to add 28691, 28691, 28691, and print that. Same thing, but now I can actually do next node. So there's this is kind of fun. I could do next node dot data is 7. But if I do next node dot data, what should it be? 2. If I just keep on doing that, you can kind of see there's 8. There's 6. So I'm just literally chaining on, I'm traversing down the linked list and grabbing the very last piece of data. This is not like, I'm just printing this just to kind of show you. Uh-oh. Did I run out? So there's 1, so that's my last one. And if I do next node here, it should be none. So this is how I literally traversed the entire tree just manually by printing it out. The heads next node is, 7, which has a next node of 2, which has a next node of 8, which has a next node of 6, 9, 1, and then the 1's next node is none. But if I do next node data, it should be 1. But if I literally just printed the next node, it'll be a node object. So this is where it kind of, you have to like traverse, all right? You've got to make sure the current node. So current node is the head, while the current node, which is currently the head's next node, while it has a value, I need to move on to the next node after that. So I'm reassigning the current node to the next node's value. So it's reassigning it, coming here, current node, next node, does it have a value? Yes. Then I'm reassigning the current node to the current node's next node, just a while loop until the next node does not have a value. And then I'm breaking out of that, and then I'm assigning the current node's next value to this new node. Anybody have any questions? I'm going to stop right there. And if you have time, I'll actually review this at the end of the day, the remove portion, because it's a little more complex because you have to keep track of the current node as well as the previous node. But